Hi kids, hope you're enjoying your snow day. It's really starting to fall down here. I'm going to make this video to review the two big ideas about the power of primes that are relevant to your homework today. Basically, let's start with the whole notion of prime numbers and what they can show us. Primes. Let's talk about 60 that has the prime factorization of 2 times 2 times 3 times 5. By looking at this, we can figure out what all of the factors of 60 are just by what we can see with our very eyes in the prime factorization. We know that 1 goes into every number, and its factor partner is 60. Looking at the prime factorization, I can also see that 2 goes into 60, and it's times the rest of these numbers. This is 6 and 5, or else we could think of it as 15 times 2. Either way, it's 2 times 30 that equals 60. The next one we want to check is 3. Now clearly 3 is in the prime factorization because we can see it right there. It's 3, and the rest is 5 times 4, or 20. The next number is a little bit harder to see because 4 itself isn't there, but 4 is equal to 2 times 2, or 2 squared. So 4 is there, and it's times 15. Clearly 5 is there, 5, and the rest is 12. And then we have 6, which is 2 times 3, so it's there. And the rest is 10. If 7 went into 60, it would have to be in the prime factorization because 7 is a prime. If 8 went into 60, we'd need 2 times 2 times 2, and we only have 2 times 2. 2 to the third power equals 8. That's worth remembering. So 8 doesn't go in. Similarly, in order for 9 to go in, we would need 3 times 3. We only have 1 3, so 9 doesn't go in. And we can see that 10 goes in, but we've already got that. So since we're in the middle, we know that we've got all of the factors of 60. By the way, because each of these has a factor partner, the only kind of numbers that have an odd number of factors are perfect squares because they would have, the factor partner would be itself, like 6 times 6 is 36, so it wouldn't have something on both sides of this line. So how can that help us with other things? Let's talk about the greatest common factor. Greatest common factor, which is the largest number that goes into a group of 2 or more numbers. So if I know that 60 is equal to 2 times 2 times 3 times 5, or 2 squared times 3 times 5, let's take another number too. 72 is equal to 2 times 2 times 2 times 3 times 3, because remember 2 to the third is 8, and 3 squared is 9. And if I were to write that in exponential form using exponents, it would be 2 to the third times 3 squared. Well, we could list all the factors of 72 and then go down the list and figure out which one is biggest. But by looking at the prime factorization, I can see that they each have 1, 2 that matches up, so they have a 2 in common. They also have another 2 in common. This third 2 isn't present in 60, so it's not a common factor. However, we also have a 3 that's in common. When I multiply these together, I can see that that equals 12, and 12 is the GCF of 60 and 72. Now, one way that you can see this is you can look at the prime factorization as well. And you can see that they have two 2's in common, but not the third 2. So we would have to use this in our greatest common factor. They also have 3's in common, but there's only one that's in both of them because 60 doesn't have 2, so there aren't 2 in common. So we'd have to use this. And by the way, if there is no exponent, that means the exponent is 1. And since 5 is not a factor, a prime factor, or a factor at all, of 72, they don't have that in common. So an easy way to think about this is to say that to find the GCF, you multiply the smallest power of the common primes. This is important to remember because it's the smallest power of the common primes. Not to be confused with the notion, the least common multiple. The least common multiple is the smallest number that 2 or more numbers goes into evenly. Wait, the smallest number, yes, that 2 or more numbers go into evenly. So, whoops, multiple. Okay, we can use the basic idea of prime factorization once again to figure out the least common multiple. So say again that I have 60, and we know that that is 2 squared times 3 times 5, and I have 72, which is 2 to the third times 3 squared. And I want to create a group of prime factors that has everything in both of these. And I want it to be the most efficient, or the smallest group. So if I look at the 2's, 2 to the third covers 2 squared. In other words, anything that's divisible by 8 is also divisible by 4. So I can put this in here. I need at least 2 to the third in order for this collection of factors to be divisible by 72. I also need 3 to the second. If it doesn't have 2 to the third and 3 to the second in there, it's not going to be divisible by 72. I can look and I can see that that number is 72, so that it would have to be, these prime factors would have to be in the collection. By the same token, I still need a 5, because if there's not a 5 in there, it's not going to be divisible by 60. So if I look here, 2 to the third, that covers the 2 squared and the 2 to the third. 3 to the second covers the 3 squared and the 3, and the 5. So these numbers multiplied together, oops, that's not the prime way, are 2 to the third times 3 squared times 5. In other words, 72 times 5, which can be a little bit hard to compute if you don't have a calculator, but if you think about it, 7 times 5 is 35. So 70 times 5 is 350, and 2 times 5 is another 10. So that makes the least common multiple 360. So the way that that all boils down is to find the LCM using prime factorization. You take the largest power of all primes, and then we multiply them. Actually, instead of saying take, let's erase that and say multiply. Multiply. Okay, the largest power of all primes. That is the LCM. In summary, it's important to remember the difference between these. The GCF is the smallest power of common primes. And the LCM is the largest power of all primes. One way or another, it's important to think about this until you've got it and can remember it. Have fun. Bye-bye.